Hello everyone. We are Group C, and the purpose of our presentation today is to discuss our work on the internal hardware of the Super Brute jack. The Super Brute is the newest iteration of the Husky Brute jack from Husky Towing's product line. The Super Brute will be updated and streamlined to reduce reliance on mechanical components by using electrical alternatives, which will reduce wear and tear as well as drive down production costs. New features for the latest model will include integrated external RGB LED and floodlight ports for simple plug-and-play use by the customer, as well as an updated interface of the mobile application for controlling and monitoring the Super Brute jack during operation.
For the requirements, the device needs to have the ability to extend and retract the jack through the Android/iOS Super Brute app via Bluetooth, or by using the physical controls on the jack itself. It should also have the ability to control the RGB LEDs plugged in by the user and change their color through the app. It will also have safety features that protect the user and the device, such as motion sensing, direction of rotation sensing, connection timeout shutoff, and a mechanical brake. The Husky Super Brute uses a brushed DC motor that operates at 12 volts and a 20 to 30 amp operating current range. It can operate all the way up to 60 amps where it reaches destruction current. The lifting capacity of the jack is 5,000 pounds. It uses Bluetooth Low Energy, which has a radius of 50 feet. It has a trailer wiring connector for the floodlight and the 4-pin main and lock connector for the RGB LEDs.
The design approach for this project was influenced by the sponsor, RV Intelligence, and the customer, Husky Towing Products. The customer wants the system to be placed within their RV jacks to control the extending and retracting of the jack. There are certain design specifications that cannot be changed because our system must be placed within their products. There are three main functions that we needed to consider when designing the system. The motor needs to be controlled to extend and retract the lift. This can be done with a brushed DC motor driver. To detect the direction that the motor is spinning, we will use a Hall effect sensor placed near the motor. With this data, we can also calculate the speed of the motor. The brushed DC motor has been provided by Husky Towing because the motors are already inside the jacks. Another necessary function to consider during the design process is the Bluetooth connection. This connection is very important because it is the primary user control for the motor. A mobile application has been designed to extend and retract the jack with an easy user interface. To ensure that the jack is level, we had to design a way to gather coordinate data. An accelerometer is a great way to determine the orientation of a device. If the jack is not level or it's in motion, it will not be able to extend. This will be an important safety feature in our design. An important aspect we needed to consider in the design phase was the dimensions of the Husky jacks. Our entire PCB, motor, and wires must fit within the dimensions shown here. The wiring within the jacks already exists, so we have to design our PCB with connectors that correspond to these wires. To accomplish the motor control, we chose the TLE92108 motor driver and the AH3774 Hall effect sensor. The motor driver is the largest component we will have on our PCB and was only released in 2019. The next largest component is the Bluetooth module. We chose the CYBLE 212006 made by Cypress because of its programmability. We can program this device to control the other devices through SPI communication. For the accelerometer, we chose the BMA 456 because it is very small with low power consumption. This component can collect coordinate data, detect motion, and measure temperature. This is a simple block diagram showing how these components will be connected. The CYBLE is a wireless module solution that offers more than just Bluetooth. It will be the main controller in the PCB. Using Cypress's IDE, PSOC Creator, the team has been able to program this device to send instructions to all the other components. The CYBLE will send signals to the TLE motor driver to determine if the RV jack should be extended or retracted. The FET network seen in this diagram is a MOSFET network comprised of 8 half bridges. The FET network will be used to power the DC motor, emergency brake, and LEDs. This is a more detailed block diagram elaborating on the one shown previously. You can see that the main components are still connected the same way with the CYBLE in the middle. This does not represent the actual PCB layout of our system, but it does show the connections and voltages needed for each component. On the bottom left corner, you can see the DC input. This voltage will be passed through a fuse and then to an overvoltage protection circuit for extra safety. Since we do not need 12 volts for all of the components, we will have a voltage regulator to decrease the voltage from 12 to 3.3 volts. This 3.3 volts will be used to power the Bluetooth, accelerometer, Hall effect sensor, and motor driver. In this diagram, we have included the connectors to connect the PCB and the RV jacks. The first connector with 6 positions will be used for the external switches. We will leave 3 connectors empty for extra connections later. The second connector with 6 positions will be used to connect the LEDs and the emergency brake. In this diagram, the floodlight refers to the external work light on the jacks. Above this diagram, we have added a magnet to signify that the Hall effect sensor will be measuring the magnitude of a magnetic field. In the actual PCB layout, this Hall effect sensor will be placed closer to the motor.
Taking a closer look at the main components in our design, let's start with the Cypress CYBLE212006, which we chose as the microcontroller for our board. It has many great features that will help us get the most out of our design. It has 2 serial communication blocks supporting I2C, SPI, or UART. It has 4 dedicated 16-bit timer, counter, or PWM blocks, which we will be using for the RGB lights. It has remappable pins, which gives us the flexibility to make our design as optimized for space as possible. And it also has a BLE protocol stack supporting generic access profile. We wrote drivers for our other components to work with the CYBLE and loaded them onto the module. At this point, our code uses 40% of the memory, which gives us room to add more functionality and revisions in the future.
Our design requires a full N-channel bridge to drive the motor, as well as a few half bridges to drive various components, such as pulse width modulated LEDs and an emergency brake. To fulfill this requirement, we chose the TLE92108-232QX, which is a multiple MOSFET driver that can drive up to 16 external N-channel MOSFETs. The TLE also comes with many other built-in features, which include reverse battery protection, 2 configurable current sense amplifiers, outstanding low sleep current, and advanced protection and diagnostic, which makes the device ideal for use in any type of motor-based lift. It has drain source monitoring for hard short circuit detection and current sense monitoring for soft short circuit detection, over temperature warning and shutdown, as well as detailed off-state diagnostics such as open load, short circuit to battery or to ground via the 24-bit serial peripheral interface. For testing purposes, we use the TLE92108-23QX app kit, which offers an easy method for connecting to the microcontroller for debugging the TLE IC. This is done through the aforementioned 24-bit serial peripheral interface, or SPI, which enables the communication between the microcontroller and the TLE through the UIO stick interface, as well as using the SPI header found on the app kit to monitor data transfer, which allows us to verify correct bit flow values on the SDI and SDO lines. The MOSFET driver IC acts as a SPI slave, while the microcontroller acts as a SPI master. Through the SPI, we can read, write, and clear multiple registers in the TLE quickly and efficiently, which allows for easily configuring the many instructions we will need to create to carry out multiple tasks the TLE will need to do, such as power on initialization, extend retract the motor, control the brightness of the LEDs via the PWM channels, and persistent status checking to ensure everything driven by the TLE is working as intended.
For the accelerometer component, we chose the BMA456 from Bosch SensorTech. This is a triaxial acceleration sensor that measures coordinates in the XYZ plane. This sensor can be programmed to fit our needs. For example, we were able to program the output data rate to a low frequency of 12.5 Hz. We were also able to configure our power mode to either performance mode or low power mode. In low power mode, the accelerometer periodically switches to a suspend power mode, in which no data is measured. We wanted our data to be as current as possible, so we chose performance mode. The sensor has a digital interface that can be configured for SPI or I2C communications, and for our application, we chose SPI. The BMA has 2 interrupt pins that send data to the CYBLE. The on-chip motion interrupt is triggered if the accelerometer senses motion. This will be used to stop the motor from running if the jack is in motion. The new data interrupt constantly sends new coordinate data to the CYBLE to ensure that the jack is level. The accelerometer is actually a very small component. To program this, we use the Bosch SensorTech shuttle board. This board is a PCB with the BMA456 mounted onto it, as seen in the second photo. The accelerometer is the small black square below those 4 pins. This shuttle board allows us to easily access the sensor pins to program the interrupts and SPI communication. In the photo on the right, you can see the CYBLE development board in the foreground. It is connected to a computer using the Cypress Mini-Prog4 debugger and programmer. In the background, you can see the BMA456 shuttle board connected to the CYBLE. This is the method that we have been using to program and debug our components.
I'm Hisham, and I'll be talking about the hardware design for this project. Starting off with the schematic, we have the voltage protection circuit, the two regulators, the microcontroller, the MOSFET driver, the accelerometer, the Hall effect sensor, the connectors, and the FETs. The TLE driver can drive up to 8 half bridges. Half bridges 1 and 2 are used to control the motor through extend and retract signals through the 6-position switch connector. Half bridge 3 is used for the brake signal. Half bridges 4 to 8 are used for controlling the external LEDs. The driver has 3 PWM inputs. The 3 PWM signals are designated for the LEDs. PWM1 is for green, PWM2 is for blue, and PWM3 is for red. A different combination of the PWM signals will result in different colors. Current from DH, which is a drain current supply, comes through the first half bridge, passes through the motor, and it then passes by the N channel of the second half bridge. A 1 milliohm sense resistor is added to measure the current passing through the motor. CSIP and CSIN are current sense inputs to the TLE. They are internally connected to an instrumental amplifier. A shunt circuit is added between the sense resistor and the current sense inputs to the TLE to protect the TLE from any high power. Our supply voltage range is between 9 volts to 20 volts. Our typical supply voltage is 12 volts. The MAX 16141A part is a diode controller that functions as reverse voltage protection circuit, over voltage protection circuit, and under voltage protection circuit. If the voltage exceeds our over voltage threshold or falls below our under voltage threshold, the part shuts down. The circuit shuts down based on the threshold that we decided, which are 9 volts minimum and 20 volts maximum. The part has a window detection threshold comparators, so by using a voltage divider circuit, we set the values of the resistors so that when the voltage changes beyond the desired thresholds, the N-channel FETs that are connected to the part will turn off. To find the values of the resistors of the voltage divider circuit, we use these equations. Sleep mode is active high. We connected sleep to a 10K pull-down resistor to ground. Pins RS and out are connected to a comparator inside the module. A sense resistor is connected between pins RS and out, which compares the current and detects any overcurrent. If any overcurrent is detected, then the module shuts off. The current threshold is calculated using a simple Ohm's law equation. VRS out is the voltage of the overcurrent threshold. R sense is the sense resistor between pins RS and out. The overcurrent threshold IOS is equal to 27.5 amps. VRS out is equal to 27.5 millivolts, which is the maximum voltage between pins RS and out that the module can handle. The sense resistor is 1 milliohm. Since the motor is rated around 240 watts, 12 volts multiply 20 amps, then 27.5 amp as a threshold is an appropriate overcurrent threshold. For reverse voltage and reverse current protection, The module measures the difference between Vin and Vout across the external FETs. If Vout minus Vin equals to 10 millivolts, then the module activates a fault that turns the gate voltage to 0. Connected to the protection circuit is a hold-up circuit, which is a circuit of 3 capacitors in parallel. 2 of them are ceramic, and one is a 100 microfarad electrolytic capacitor that functions as a reservoir. The hold-up circuit is connected to a 12 volt to 3.3 volt regulator and a 12 volt to 5 volt regulator. The small signal ICs have a nominal voltage of 3.3 volts, and the 5 volt regulator is for the external LEDs. The 5 volt regulator is enabled by the microcontroller through an enable circuit that we designed. The circuit is mainly consisted of a P-channel MOSFET and an N-channel MOSFET, which has its source connected to ground. V2 in the simulation is the enable signal coming from the microcontroller and also the gate to source voltage of the N-channel MOSFET. Simulating the circuit, when V2 is 0, the voltage at the input of the regulator becomes 0. When V2 is enough of a voltage, the voltage at the input of the regulator becomes close to 12 volts. As for the connectors, we have a 6-position connector for the switches, which are light 1, light 2, extend, retract, and break. Light 1 and light 2 are for the LEDs. When the switch is turned on, the signal on the microcontroller is shorted to ground. Since the GPIOs for the microcontroller are active low, then the microcontroller now has a signal. We decided to use 5 single vertical connectors for the external LEDs. And as for the power supply and the motor, we decided to use single horizontal connectors. To each connector, we connected a transient voltage suppressor to prevent any spikes in voltages. As for the PCB, we decided to design a 4-layer board. The top and the bottom layers are for power traces. The second and third layers are for signal traces. We filled the top and the bottom layers with ground. For signal ground, we designated the bottom lift area where the radio is located to be signal ground. There are 3 5mm screw holes. One at the top left, one is to the right, and one is near the bottom. We designed the board so that the power supply will be connected to the bottom right of the board. There is a drill hole at the bottom right and an hitch cut for a zip tie to hold tight the 3 high current wires, which are 12 volt supply, source current for half bridge 1, and source current for half bridge 2. Power traces have a track width of 3 mm. However, we avoided connecting the high current components with traces. Instead, we created different zones for different high power components such as 12 volt supply, source current 1, and drain current 1. Each zone on the front copper has its identical sister on the back copper, and they are connected together through stitching vias. We placed the TLE as close to the middle of the board as possible, so it's close to the FETs at the top and the radio at the bottom. We placed the radio in the very bottom, as far from the high current and the motor as possible, to avoid radio interference. The max part is placed between the TLE and the radio. The 6-position connector is located above the TLE, and the LED's connectors are placed at the top of the board, close enough to the FETs that are assigned to control them. What went wrong in our design? We designed a protection circuit to every switch signal to protect the microcontroller from any high voltage. The circuit consisted of a transient voltage suppressor, a Schottky diode, a pull-up resistor to 3.3 volts, and a series resistor. When the switch is turned on, we get a voltage of 2.4 volts at the anode of the diode, which is too high to enable the GPIO, which is active low. As a result, there's no signal activated through the switches. What we did is that we removed the 3.3 ohm resistor. Another issue that we faced is that the MAX 16141A protection circuit always gave a fault when we tried to start the motor. The part activates a fault if Vout is less than 90% of Vin. To solve this issue, we tracked Vn, Vout, Vin minus Vout, and the fault signal. The fault signal is active low, and it went low as Vin minus Vout was more than 10% of Vn. We jumped the wire over the protection circuit to the regulator.
As for the software design, the main program operation will go as shown in the following flowchart. First, we will begin by initializing all of our components, enabling interrupts, and starting the SPI and UART. Then we will go into our main loop. We begin by checking the connection status of the device. If the device is connected to a phone, it will then run the function flag handler. This function checks if any of our flags have been set by the interrupt lines and calls a function to handle it. After all the flags have been taken care of, we can start the main loop over again. For the software controlling the TLE, the structure of the driver is as follows. The high-level calls such as spin motor, brake on, RGB on are in the file tle.c. Those functions called the tle_driver.c functions, which use hex values defined in the file tle-regs.h to build the required packet to make the action happen and send it over to SPI lines. So for example, to extend the jack, the flag handler in main will call the function spin motor clockwise in tle.c. That function then calls the functions half bridge 1 high side on and half bridge 2 low side on in tle_driver.c, which sends that configuration to the half bridge control register on the TLE.
The software design for the accelerometer was created using the API provided by Bosch. Before we could use the data, the accelerometer had to be initialized. This initialization function created a struct to store various parameters for the BMA456 device. These parameters include the chip ID, communication interface, pointers to the SPI functions, read and write length, performance mode, and many more. The initial design seemed straightforward, but the documentation for the BMA456 was lacking in some areas. Writing the configuration file took a very long time to accomplish because of the SPI read and write functions. I had to write my own SPI functions to work with the provided API. The datasheet did not specify that 2 dummy bytes are used for the BMA SPI interaction. This extra dummy byte caused a delay, but once we figured it out, my SPI functions began to work. The configuration file also caused an error because we did not have sufficient delay time between the write calls. The Cypress Bluetooth module needed a larger delay time than the API originally provided. Mapping the interrupts also seems like a simple task, but the API provided did not explain this process, and it took a great deal of research to figure out the correct mapping. I correctly mapped the interrupts by writing directly to the registers at first, but we eventually figured out the correct parameters to pass to the API's mapping interrupt function. The new data interrupt worked immediately after mapping these interrupts correctly, but the motion interrupt took longer to figure out. I finally got the motion interrupt to work by reading the status register, which automatically cleared the interrupt. Without this, clearing the interrupt myself and clearing the pin was not sufficient. Throughout debugging the accelerometer, I used a logic analyzer because it was essential to fixing the SPI and interrupt problems. Once we were able to read the data from the logic analyzer, we could see exactly what the modules were sending back and forth. The design for the Hall effect sensor did not require an API because there is only one output. If the Hall effect sensor detects a magnetic field, it triggers an interrupt and sets a flag. We read this interrupt on both the rising and falling edge of the pulse. We place the magnets about 120 degrees apart so that the pulses are not of equal length. When the south pole passes over the magnet, the pulse is low. When the north pole passes over the magnet, the pulse is high. By detecting the previous and current level of the pulse, we were able to determine if the motor was spinning clockwise or counterclockwise. This provided an extra safety feature to make sure that the motor does not extend or retract too far. The team met together several times a week to ensure this project was completed correctly. Everyone worked together to make sure that the software and the hardware teams were on the same page every step of the way. We would like to thank Herb Gingold from RV Intelligence
for sponsoring our project and spending his time teaching us valuable information. We will be starting our careers with many more skills than we had at the start of this year.